Good morning, ladies and gentlemen. Welcome to my office at home. I've been directed to work from home, so for the next couple days at least. So that means we are here. So please excuse the poor lighting. I know it's like really bright, but lighting is not the best in here. Will admit my dog is incredibly happy that I'm working from home, so I do apologize if she comes up and like sticks her snoot on my desk or something like that. So hey, Freya's happy. All right. So, ladies and gentlemen, what we're going to be working on today is going to be our force of friction. So if you guys can please make sure that you guys have your force of friction notes out, and you should have on your copy, you should have a couple of awesome memes. My personal favorite is the two cats when they're on a roof. Which one's going to fall off first? The one with the lowest mu. Well, mu is the symbol for coefficient of friction, which we're going to be talking about today. So we are going to be talking more about friction itself and how we can calculate friction independently from our lovely force net equations. We're still going to use those too, but right in an extra pace. Yeah. So you guys excited? Gonna rock from physics? Yeah. Okay. All right, so ladies and gentlemen, we're going to select a pen. Now bear with me, I'm kind of writing it, and here's the computer and here's the tablet thing, so I'm going to be back and forth a little bit. Okay, so keep in mind, ladies and gentlemen, that friction is going to be when you have two surfaces that are going to be rubbing against each other, and it is going to be the force that opposes motion, so we're preventing motion from occurring. Now, there's two kinds of friction. So static friction. Now let's think about the word static. Static means to not move. So this is where you have stationary objects, so objects that are not moving. And that is the minimum amount of friction that is going to be needed to be overcome to get an object to move. Okay. And kinetic friction. Now think about the word kinetic, as in kinetic energy, which is meaning your motion. And this is going to be occurring between objects that are already in motion, and it's going to be preventing them from continuing to move. It's going to oppose them from moving. Okay, let's scroll up a bit. And now we have our new item of the day, ladies and gentlemen, is our coefficient of friction. Now, this is your ratio in between your force of friction and your normal force. So essentially what it is it's a measurement of how rough something is. So if you have, for example, where's my pen here? There you go. The name of the symbol, this little U guy, is called mu. Okay, it's pronounced mu. So which cat falls off the roof first? The one with the lowest mu? The one with the lowest coefficient of friction? Come on, you laughed. Okay. And mu is essentially an indicator of how much friction is present. So if you're going to have low mu, it means it is going to be a smooth surface with very low friction. And if you have high mu, that means you are going to have a rough surface. So when we're done this video, we'll do a field trip to my kitchen floor and to the carpet of the spare room. So great places for a field trip, right? But we will then compare our forces of friction, and I guarantee my dog is definitely going to show up to check out what's going on for our field trip, so you can all officially meet Freya. Okay, so when this video is done, you can go check out the other video, or pause this one now, go do my kitchen floor and spare room floor field trip video, and then you can always come back to this one after for our calculations. Okay. Oh, hi, Freya. Okay. So let's look at our equation here. So your force of friction is equal to mu Fn. Now this equation is on your data sheet. Okay, so you can find it quite easily there under that dynamics section. And force of friction is, of course, in newtons. Okay, that's not news. And your normal force, also in newtons, not news. Remembering that our normal force is the force of the ground pushing up against that object. Okay? And mu is our coefficient of friction, a representation of how rough or how smooth something is. It is unitless. So ladies and gentlemen, when I ask you to calculate mu, I am not going to want to see any units there because there are no units. All right, and I can show you how that works a little bit later. Okay. Ladies and gentlemen, as we talked about already, I can put a little star here, mu is going to depend on the nature of the surfaces, and that's where we're going to do our field trip to my kitchen floor and field trip to the spare room video. Yay, field trip. Okay. So, ladies and gentlemen, okay, we have your US or mu s, that's your coefficient of static friction, and it's going to be the conditions just before an object starts to move. Okay, and that's called our threshold of motion. Now, let's think for a minute here, guys, our little question here. Now, our coefficient of kinetic motion is smaller than the coefficient of static friction for the most part. Think about it for a second. I want you to think about why that may be the case. Pondering. Pondering. Do you have an answer? I can't even wait to hear you guys yell out answers again. It would be pretty darn cool. Okay. So I hope you guys have an answer. And our answer is Newton's first law. So let's think about Newton's first law. Newton's first law is your laws of inertia. So objects at rest have a tendency to stay in rest. So an object that is at rest is not going to be interested in moving that much. So it's going to take a bit of effort to get it going. Once an object is in motion, it's going to want to stay in motion. So you're going to have to take some effort to stop it. Okay? So your objects at rest tend to stay at rest. So therefore, you're going to have more effort to get an object moving. Okay, so same with your object in motion. An object in motion is going to take more effort to get it to stop because it's going to want to continue moving because of Newton's first law. Cool, eh? I think it's pretty cool. All right, so we're going to scroll down, and are you guys excited? We are going to start some math. Woo-hoo! Okay, so we have a team of, let's select our pen here. A team of 10 sled dogs is pulling a dog sled at a constant velocity of 8.1 kilometers an hour over the frozen tundra. Now let's take this moment to talk about the term distractor. We had a ton of info in here that is not going to help us here. And that does include things like 10 dogs. Do we really care that there's 10 dogs pulling this sled? I mean, dogs are pretty awesome. You know, I've got one. But that's not a relevant number to our calculations. Now, what we do have here, though, is the term constant velocity. What that tells us, recall, is that our F net is going to equal 0. So that's actually more important than our numerical value of 8.1 kilometers an hour here. So, sorry, that's the dog. Okay, she's throwing her antler around the kitchen, apparently. That's a great thing to do if you're a dog. And now she's throwing her bone in here. Okay. So we have a mass of 1,000 kilograms. That is going to be relevant. Hi, Freya. Hello. Here's your bone. And you want to come here and say hi? Hey, come here. Come here. Can you guys see the snoot? There's the snoot. Hey, there she is. Hi, Freya. Hello. Here's your bone. Yes. There you go. You go chew your bone. Okay, we're going to chew her. She's going to chew her bone on my lap because that's apparently the best place to chew a bone. Okay, let's get back to our calculation. We've had a puppy break. Freya, your bone's over here. Okay, come on. There you go. Chew bone. Okay. All right, so the mass is relevant, and the fact that our F net, that should be an F, is 0 newtons, that is relevant. That also means our acceleration is going to be 0 meters per second squared. Okay, let's see what else we have here. Calculate the coefficient of friction. Okay, so that means our mu is going to be what we want, and keyword kinetic as well. So we're looking at the object when in motion. And between the dog sled and the snow, if the dogs must exert a total force of 922 newtons to keep the dog sled traveling at a constant velocity. So what that value is going to be your force applied. Okay, so first things first, let's draw our beautiful diagram. Here, come on, Freya, chew your bone. You chew your bone. Okay. Oh, hi. Now we're going to chew the bone on my lap again. Okay. So we have your dog sled. We are going to be having your force applied, and we are going to be having our force of friction. Now, keep in mind, ladies and gentlemen, that because we're going at a constant velocity, we want those arrows to be of the same size. We are going to be dealing with our normal force now. Because we are not accelerating either up or down, our Fn and Fg arrows are going to want to be about the same size. Okay. So, ladies and gentlemen, let us... Oh, force applied. I did not write down our force applied. That's not a question mark. That's 922 newtons. Okay, go chew your bone. Go play with your bone. Okay. Okay. So let's do a bit of planning here, ladies and gentlemen. We have been asked to calculate our force, or excuse me, our mu. So our equation in order to get mu is our force of friction is equal to mu Fn. Okay, well, at this point, we don't have our force of friction and we don't have our Fn. So we are going to have to calculate both of those before we can do anything else. So we have, let's start with our force of friction because we can. Why not? So let's think about our forces on that x-axis. So we're going to make an F net equation on that x. So our F net is going to equal our force applied minus our force of friction. Now remember, our F net is going to be 0. So that's going to cancel out. So there, and then we can add our force of friction over on both sides. Okay. Here, scroll down a bit. There we go. Okay. So I'm going to wind up with my force of friction is going to equal my force applied. So, well, I already have my force applied. So that means my force of friction is going to be 922 newtons. That value we can get specifically because of that term constant velocity. We're not accelerating at all, no acceleration whatsoever. So that tells us that we have our F net is 0. Okay. Now let's come over here and get our Fn. Now Fn is on the vertical. So let's make an F net equation on the vertical. And so we have our normal force minus our force of gravity. Well, this dog sled is not accelerating up through the air nor sinking through the ground. So that means the forces on the vertical are also going to cancel out. We are going to have an F net on the vertical of 0 newtons. So I'm going to add my Fg over onto this other side. So my Fg is now going to equal my Fn. Well, guess what, ladies and gentlemen? We have the mass. We also have an equation that is going to help us with our Fg. Well, Fg is equal to mg, so I am going to replace that Fg with an mg. Okay, so I can get my normal force by timesing that mass of 1,000 kilograms times 9.81. Okay, so once you do that, you are going to wind up with your lovely value, 9,810 newtons, okay, is our normal force. So, well, now, ladies and gentlemen, we have force of friction and we have normal force. We can now reorganize our equation in order to isolate from mu. So I'm going to scroll down a bit so I've got some more space to write. So my force of friction is going to equal mu Fn. And I'm going to try to get that mu by itself. So I'm going to divide out Fn on both sides. So that way that cancels. So mu is equal to force of friction divided by Fn. Okay. Now I'm going to plunk my numbers in, and I am going to wind up with my 922 newtons. And we're going to divide that by 9,810 newtons. So let's pause for a moment here, ladies and gentlemen. Remember how I mentioned earlier, I would tell you guys why mu has no units? And here it is. So when you look at this equation, notice our units cancel here. Newtons divided by newtons is 1. So that means this value is going to have a unitless number. Okay. So when you put this number in your calculator, you're going to wind up with mu 0.0985 ... Well, now let's go look at our sig digs. Go back to our original question. We're only going to use the sig dig values that we actually use in our equation. That's another key piece to watch out for distractors. Is that 8.1 kilometers an hour is completely irrelevant. It's a distractor. We didn't use it, so we don't use that for sig digs. And our mass of 1,000 kilograms, well, we use that. That's 4 sig digs. And then 922 newtons, well, we use that. That's 3 sig digs. We didn't use the 10 sled dogs, so we don't use that. So that means I want 3 sig digs. Okay, so I dropped a 3 here. Oops, there we go. So you're going to wind up with your value of 0.940 once you have done your appropriate rounding. Mu is scalar. Mu is unitless. So I dropped another 0. Goodness gracious. There we go. Mu is scalar, and mu has no direction, no units. So I don't want units. I don't want sig digs. This is probably one of the only cases where I will actually deduct points if you put units. Correction, I don't want sig digs. I do want sig digs. I don't want units and don't want direction. Probably one of the few times I will deduct if you give me units. Okay, don't give me units on mu. There's mu. Okay. Ladies and gentlemen, if you have questions, fire me an email. Okay, let's switch over to our tool there. All right, so let's look at our next question here. So I'm just going to erase this random mu that's just hanging out there. Back to pen. Okay. So, ladies and gentlemen, a 7.6 kilogram object is pulled along a horizontal surface. If the coefficient of friction between the surfaces is 0.20, what is the magnitude of the force of friction? Okay, well, let's list out what we have here. So we have the mass of 7.6 kilograms. We have mu of 0.2. And then we have And not much else. You have gravity of 9.81. You could write that down if you want. Okay, well, let's draw ourselves a free body diagram because it's what we always do. You guys will notice I'm getting better at this thing after all the videos. I can actually draw a box that looks kind of like a box. So we have the thing is that we do not know about a force applied here. We don't know if we have a net force. We don't know if it's going to be longer than our force of friction arrow. We just don't know. Okay, so we absolutely know we have a force of friction. We have been given mu. We absolutely know we have an Fg, and we absolutely know that we are going to have a normal force. Okay, so let's think about this for a sec. Well, I can't use my F net equation here because I don't know anything about a force applied. Okay. Okay. On X as no force applied. So we have no data about it at all. So we can't build a force net equation right away here. But what we do know is that our force of friction is equal to mu Fn. So we are trying to find our force of friction here. And we have mu, so what we need to do now is we're going to need to calculate our normal force here. So we can make a force of friction, an F net equation on the y. So my F net is going to equal my Fn minus my Fg. So because this object is not accelerating up through the air nor sinking through the ground, our forces on the y are going to cancel out. So my F net on the y is going to be 0 newtons. I'm going to add my Fg over here. And I'm going to wind up with my Fg is going to equal mg. Looking familiar, guys? Yeah. Okay. Because Fg equals mg, and my equation is going to equal Fg equals Fm. Well, I can take this mg and just replace that Fg with the mg. Okay, I'm going to scroll down a bit here. There we go. All right. So my Fn is going to equal mg. So we know the mass of this object is 7.6 kilograms. We know g is 9.81 meters per second squared. So my normal force is going to be 74.556 newtons. Leave all numbers in your calculator, ladies and gentlemen. Do not round at this point. Well, I now have my Fn. So now I can put all my values into this equation here. I already have mu. So my force of friction is going to equal mu Fn. My force of friction is equal to my mu of 0.2, and my force of friction of normal force, beg pardon, of 74.556 newtons. Plunk that into your calculator, ladies and gentlemen, and you're going to wind up with 14.9112 newtons. So your force of friction is now going to be equal with your sig dig. Let's come back to the original question. 7.6 kilograms and 0.20 are our values, so that's 2 sig digs. So I'm going to wind up with 15 newtons. Now, when you also look at the original question, it says, what is the magnitude of the force of friction? Because the question says magnitude, it means I don't want you to tell me the direction. So we leave that as it is, and we box your final answer. But I am. Okay. All right. So let's scroll down to our last question of the lesson. Okay. Now, this one is actually really fun. I like this one. which generally means the second I say that, you guys start cringing in fear because it means the long question. Which is true. This one is long, but it's so fun. It's super cool. Wrong tab. There we go. Okay. So let's make a plan of attack. So our mass of a car is 895 kilograms, and it is traveling at 14.1 meters per second along a level but icy road. Okay. So, well, that's our initial velocity, ladies and gentlemen. So 14.1 meters per second. Now, ladies and gentlemen, let's think about icy for a sec. That's going to be something that's going to help us out. Because when you have something that's icy, what's going to have that mu going to be, higher or lower? Lower, exactly. Because the lower the mu, the lower your force of friction is going to be. So if something's icy and there's not much friction, you're going to have a lower mu. Okay? So when you check your final answer, you want to make sure that mu is going to be a small number. Okay. And the wheels are going to lock, and the tires are going to skid along the icy surface. So which means someone did not have ABS or was driving like a schmuck. Don't drive like a schmuck, guys. Drive normal. Four-wheel drive does not help you stop. Four-wheel drive helps you get started and prevents a little bit of lateral shimmying. So if the roads are icy and you drive something with 4x4, you're not invincible. Slow down. And because you have a larger mass, it means you're going to have a larger FG, which means you're going to have a larger normal force. Yeah. So sure, there'll be more friction, but we can also do a whole bunch of math on how you're going to have a lot more momentum. You're going to have a larger mass. So seriously, guys, if you're driving a truck with 4x4, just slow down. Truly. Truly. You need much larger stopping distance. Okay. Back to this. So we travel a distance of 24.6 meters before coming to a stop. That's a pretty big distance, guys. So slow down. Okay? Slow down on icy roads before coming to a stop. So stop. That automatically tells us, as we know from our kinematics unit, which you guys got to miss out on the unit test for, is going to be 0 meters per second. Calculate the coefficient of friction between the car's surface and the ice. That is a really ugly mu. Let's try that again. Cool, I can switch pens by just touching the little tab at the bottom. Sick. I just learned a new thing. Okay. So, there we go. So we need to calculate mu. Ladies and gentlemen, this is a tough question, and it's going to involve a bunch of planning on our part. So let's think about what we have. So first, let's draw a Freebody diagram. There's your car. Hey, let's draw a surface. Why not? So the car is going to have no force applied. As the car is, this guy's not stepping on the gas. He's stepping on the brakes. So he has no force applied on his car. But as when you brake, you are just increasing the force of friction between the vehicle and the road. Oh, come on. Well, not between your vehicle and the road, excuse me, between your vehicle and its wheels. So we're going to have our normal force. And we have our force of gravity. Okay. So let's think here. We need to plan before we do math. I've asked you guys to calculate mu. Well, we know that our mu is equal to the force of friction times mu Fn. Okay. Well, we need to do a bit of thinking here. So we know that we're going to need to calculate our normal force. Well, that part we already know how to do, so we can just do that right now. Okay. So we can make an F-net equation on the y, which is going to mean that our F-net is going to equal Fn minus Fg. So because our car is neither accelerating up or accelerating down through the ground, it would mean our F-net is going to be 0 on the y. And I can add my Fg over. So my Fg is going to equal my Fn. And Fg is equal to mg. So that's my normal force. So my normal force is going to equal I'm going to scroll down so I don't have to write on my face. There we go. So my normal force is going to equal my mass of the car, which is 895 kilograms. And we multiply that by 9.81. So my normal force here is going to equal 8,779.95 newtons. Okay, so I'm going to leave that value there for now, and then we'll come back and use it later. Because in the meantime, we need to figure out our force of friction here. So let's think about our force of friction. And let's think about our net force on the x. What's our only force on the x? Force of friction. Now the car is slowing down. So what type of motion is this? Accelerated. Excellent. The motion is accelerated motion. So that means, are we going to have an F-net? We absolutely will. So we can write our F-net is going to equal our force applied and our force of friction. Well, hold on a sec, you say. We don't have a force applied. So let's get rid of that. We don't have a force applied. We only have a force of friction here. So, ladies and gentlemen, our F-net is going to equal our force of friction. But because we're going to be dealing with our deceleration and our motion is going to be going this way, okay, so that's where your velocity, or excuse me, your speed's going this way. Because your speed's going that way and acceleration's going this way, our force is going this way, our force of friction is going to be a negative value. Okay, and we want that, okay, we want that to be negative, right? Well, okay, well, we have this. This is great, but now what? Well, what about F-net? Can I find that a different way? How can I find F-net? What's our famous F-net equation? What's Newton's second law equation? Mass times acceleration. So I can replace my MA is going to equal my force of friction. Well, I am going to need to find my F-net here. So, okay, well, I have the mass. Well, darn. I don't have acceleration. Despair. No despair. Come on. How do we find acceleration? Do not despair. How to find acceleration, guys? Come on, acceleration! Exactly. What are your kinematics equations? So you're going to go to your data sheet again, your beautiful data sheet, and you're going to look at those 5 kinematics equations that I asked you guys to circle early on in the day. And I know you guys will be allowed to get your go to your lockers and such over the next couple days, so you should be able to get all of your physics stuff. So you should have your notes and your data sheet in there. And if you don't have it, email me and I'll email you a copy of your data sheet. So let's look at our beautiful data sheets, and we're going to pick one that has some of the information that we need. Well, we need A, so we need an acceleration equation with A in it. We have D, and we have VF, and we have VI. So, well, I'm going to get acceleration from VF squared is equal to VI squared plus 2AD. I can now find acceleration here. All right. Whew. We got a lot of work ahead of us here, ladies and gentlemen. Okay, let's start by finding our acceleration. Okay, so I'm going to scroll down a bit. I'm going to leave some space here. So my first step that I'm going to need to do on this side, so I guess we did this one first. And then we'll have 2, and then 3, and then 4, and then we can do this step 5 up there. Okay, so we've already done step 1. Now we're going to come down here and we're going to do our step 2. Well, I need to rearrange this guy. So my VF squared is equal to VI squared plus 2AD. Well, my VF squared is 0 because our VF means we're come to a stop. So that means, well, I've got 0 is equal to VI squared plus 2AD. Well, I'm going to go and use my reverse BEDMAS, and I'm going to subtract out my VI squared on both sides. Okay, don't drop that negative, ladies and gentlemen. Remember, those negatives come really important with our direction, so watch out for that, okay? So our negative VI squared is going to equal 2AD, and I'm trying to isolate acceleration, so I'm going to divide by 2D on both sides. I will scroll down. Okay. And that should be the 2 I crossed out, not the A. So my acceleration is going to equal negative VI squared divided by 2D. I'm going to now calculate my acceleration. So my negative and my VI is my 14.1 meters per second. I'm going to square that. And we're going to divide by our 2 times 24.6, so your distance from earlier. So once we solve for this here, we are going to wind up with a negative acceleration, which is exactly what you want because we're slowing down. We want that negative acceleration. So our acceleration is going to be negative 4.04085 meters per second squared. So use all of those numbers, ladies and gentlemen, in your calculator for your next step. Okay, so our next thing is we're going to need to calculate our F net, as our F net is going to equal our negative force of friction. So I have space up here, so I will just scroll up a bit. Oh, how'd that happen? Okay. Well, that sucks. Darn. We are back, and with our brief interruption of the technology failing us again. Story of my life. So we're going to keep going with this question and where we left off. And unfortunately, we're not going to have everything written down. Unless you want me to rewrite everything again. So where we had left off is we had calculated our Fn, so you can see how we got that in the previous portion of the video. And we calculated our Fn to be your 8, goodness, let's try that again. With an eraser, there we go. With an 8,779.95 newtons. So you can see where we'll get that from our previous section of the video before our tech died and killed all our work. So we calculated our acceleration, as we saw in the first section of the video, to be your negative 4.04085 meters per second squared. So that was about where the video killed all of our hard work. So the next piece that we are going to be looking at now is how to use our acceleration. So keep in mind that from all of our previous work that our F net equaled our negative force of friction. Well, we have acceleration now, so we are able to get our F net. And ladies and gentlemen, F net equals MA. So MA is going to equal my negative force of friction. So the mass of the car, which we had earlier, is our 895 kilograms. And we're going to multiply that by our negative 4.0485 meters per second squared. Okay. So now our force of friction is going to be the lovely number of, oops. Okay, which is going to be our 3,616.564 newtons. Now notice what I've done here. Well, there's this negative here and there's this negative here. I multiplied these two together and I got a negative number. Well, that leaves us with a negative force of friction. So we have a negative and a negative, and they both cancel out to be a positive. So that's why I did that there. Okay. Well, now that we have our force of friction and we have our Fn, we can now calculate our mu. So my force of friction is equal to mu Fn. And mu, I'm going to divide out my Fn on both sides to get my mu. So mu is going to equal force of friction divided by my normal force. So I'm going to put my numbers into my equation. And that is going to be my 3616.564. You're going to use all those digits from your calculator, ladies and gentlemen, including that of your Fn, which we calculated earlier, which you get is an 8779.95. And we're going to wind up with mu of 0.4191 ... So go back to your question now and let's look at our significant digits. So I want 3 sig digs. So I'm going to round this to 0.412. Now, this is the only time I don't want units because this is a unitless number. If you put units here, I deduct points. No units, go with mu. Okay. And now we box our final answer. All right. So ladies and gentlemen, we have your series of practice problems here. So you can give a couple of those a try, do enough of them until you're comfortable to go chip away at your assignment. And then we've got a couple more practice problems here for you guys to have a crack at too. So ladies and gentlemen, our next video is going to be the field trip to my kitchen floor and the carpet of my spare bedroom. And that'll be our force of friction lesson. And then after that, we've got pulleys and systems, and we'll be halfway done dynamics. All right, ladies and gentlemen, we will catch you on the flip side. There you go. See you later.